Thanks for coming to my talk. My name is Ignat, I work for Cloudflare, and today we're going to talk about performance and security. So if you're even missed and you're in the wrong track and you wanted something about performance, you will get it as well, so don't worry. A little bit about myself. I do performance and security at Cloudflare. I also am passionate about cryptography, and I enjoy low-level programming, so like Linux kernel bootloaders and other low-level, scary, unsafe things. Okay, so performance or security, right? What is more important? How many of you have found themselves in this scenario where, like, who here are security engineers? Okay. The rest is performance, right? So like on the one hand, you have the rest of the organization, and usually organization drives for performance. So because you just get better like returns if you have better performance. And there is always this pesky security team, right? Which is like, oh, you need to secure systems, you need to add this and that. And that sometimes that adds overhead, and we're continuously in this war, like what is more important? Like, there are like organizations which try to balance that somehow. So like, there is always a trade. They recognize there should be some trade-off. We should add some security. We should but really care about performance as well. But the purpose of this talk is like, people miss opportunities that sometimes you can have both, and like one helps the other. And we will go into explore what are the potential security improvements which might give you performance. But before we start, let's fix some terminology. When we talk about performance, most people think performance like in the narrow sense, which is usually speed, throughput, or latency, right? So sometimes you need to consider performance in the broader sense, which includes all the above, but also you have some resource optimization. We have process optimization or something else. Well, performance improvement basically means if you can get more for the same cost, right? So anything more. Or you get the same for less, so it doesn't matter. Okay, so let's start simple, right? Like we're not going to jump security things which improve performance. We just, first of all, there are many security things which have zero performance overhead. So I call it zero cost security. And I'll just, throughout this talk, I'll just walk through all the examples we encountered in Cloudflare, and there are actually a lot of other ones, and there is a lot of potential elsewhere, but all of these examples you might find useful and implement them in your company. So what does mean zero cost security? There are several things which fall into this category. So first of all, it's when this actual security cost is negligible, or it affects something, but it's a non-primary metric. Also, security cost may be just hidden or amortized by the architecture of the implementation. And finally, security cost is not incurred by normal system behavior. I call it so-called prohibitive security. You will understand later why. Okay, so let's see the example of negligible security cost. Cloudflare, we operate a large network, and due to the nature of our business, we need to run on real hardware. We can't use any cloud providers. And one of the things we implemented is secure boot. We have a lot of servers throughout the world, they boot, and we need to ensure that boot is secure. So anyone here knows how secure boot works or doesn't know? Okay.
So the question is no or doesn't know?
No? No. So secure boot is a simple concept. So it usually starts with some kind of trust anchor, which is on the server. It's like a system firmware, which is sometimes called BIOS. So when you enable the feature, it's basically the BIOS can verify your primary bootloader before executing it. So when you verified it, now you trust that bootloader, right? So then you trust that bootloader to verify your operating system kernel. And now you extend this chain of trust to operating system kernel. Then, because you trust your operating system kernel, you trust it to verify its drivers and applications. So in the end, you build yourself a trust chain, or they call it secure boot chain. And in the result, all running software on your systems, even their remote, is signed and authorized by you. So secure boot basically has advantages, right? So it ensures that all running code on your system is authorized by the system owner, by you. But and it's basically, it's the most efficient protection from persistent malware. So if your system gets compromised, if somebody gets and exploits a vulnerability in your system, the first thing the attacker would do is to ensure they're persistent, right? So then when you reboot the system, they can regain their control. And secure boot is one of the most efficient features, like to disable that possibility for the attackers. But it also has some non-security improvements, right? When you can only run authorized and signed software on your system, it enforces your operational procedures. So this is kind of performance improvement in the broader sense. And so because now your operations team has to always go through the version and control system to do any changes for the system, and they can't do one-offs. You know, sometimes when operations people debug an issue, they kind of fix it locally and forget to go through the whole process and like make sure that fix is replicated to your network, and then your fix is lost. And also your systems run only what's needed. So again, your operating staff cannot run their software like software one-offs on the system. And with the negligible security costs, adding security costs does not add overhead to the running system, because all images, all signatures are checked at boot time. So it affects system boot time only. It's a non-primary metric. And like even then, like modern servers, like for us, it takes them like actual minutes to boot up and get all the config and start serving production traffic. So, and signature checking is actually adds less than a millisecond to the boot time. So it's negligible. Okay, as a second category, it's amortized security cost. Let's talk about data encryption at rest. Who here doesn't encrypt data at rest? Good. Ah, you don't?
Doesn't.
You don't? You don't? Why not? It's not important. Okay. So how does data is stored? Let's review the software stack. You have your application or services. They usually write some kind of files. And like file system care about files. Then file system translates those files into data blocks and send to your operating system block subsystem, and then the blocks are getting stored in the hardware, right? And if you want to encrypt data at rest, you can do it at these various levels. So you can actually just buy self-encrypting disks, which is quite easy. You can use your operating system full disk encryption. You can encrypt actually. In Linux, you can encrypt data directly in the file system. Or, of course, you can just like add code to your application which encrypts data before writing it down. So in Cloudflare and like many other SaaS businesses, we prefer operating system full disk encryption for different reasons. So mostly because it's very easy to set up and no configuration needed. It's fully transparent to applications, so applications do not even know that they are writing encrypted data, so data gets encrypted automatically. We don't roll our own crypto, so if instead we do it in the application layer and we go to each developer asking them to add some cryptography in their software, it usually goes wrong, right? So, and unlike a hardware layer, it's open source, so we can see and audit the code and make sure it works properly. Like even Microsoft these days prefers software disk encryption over hardware disk encryption because of the latest vulnerabilities found in hardware disk encryption. So disk encryption is a typical example of amortized security costs. Let's say if you follow the traditional model of a service, right? So if you have a server and you have like many users across the internet, the disk encryption does add the overhead, but that overhead is usually amortized by the network latency between your users and the server. So like users most likely will not notice that overhead. It's a bit different for us. So Cloudflare, one of the main Cloudflare offerings is a CDN. So this is where we try to bring our service as close as possible to users. And we're very close, actually. So like this, oh, you don't see the map. OK, imagine there is a map here. The gist is we have a lot of data centers across the world, more than 200 now. And like each major city with internet user has their data centers. And this is where the overhead of disk encryption starts to get noticed by the users. And at some point, it was so noticeable where our users started complaining, and we tried to look into it. And basically, we found that disk encryption does create like visible overhead. So this is our average CDN cache response tail latency. So we did a like A/B test, and you can see that the latency from an encrypted server like is much more spikier, and you can see it clearly stands out. So we tried to look into this problem, and we just came up with it just was released last week, with a patch to Linux kernel, which just improves disk encryption performance. I plan to run a blog post about it, but I haven't done it yet. But you can check my presentation from last week, and it includes link for the patches. It's quite interesting in its own. But the gist here is that when we developed the patch, we expected to improve performance, but we still expected to see some overhead, because you definitely need to have some overhead with encryption compared to things without encryption, right? But in the end, the result was like more not that we expected. So the blue line here is in our patched encryption implementation, and it actually doesn't do any overhead in our CDN cache tail latency. So yeah, we expect a lower disk encryption overhead. So we discussed like what kind of overhead is acceptable to balance between performance and security, but we actually got none. And our patch doesn't change any crypto algorithms or formats. It just changes the way the architecture in the Linux kernel disk encryption implementation. So we deployed it immediately. Like zero overhead data encryption is a no-brainer. But the thing is, what we learned that if we don't see any overhead of adding disk encryption, that encryption is not a bottleneck anymore, right? So probably there is something else in our systems which is bottlenecking our tail latency now. So this security improvement not only like added security, it also encouraged us to review our CDN architecture to actually seek these other bottlenecks. So we want to get to the point where we see some overhead from encryption. Finally, prohibitive security, system calls. Let's talk about system. Who here doesn't know what a system call is? System calls. So you have as usual, you have your applications and services. They don't run standalone. They run on some kind of operating system, and it's usually, we run on Linux. So. And application cannot do stuff on their own. They need the operating system to do stuff on their behalf, like writing files and sending data over the network. So operating system has a well-defined interface for application to do that, and this well-defined interface is called system calls. So application just calls that interface into the operating system. So here you can read files and send data over the network. So Linux have this nice thing called seccomp. Who haven't heard about seccomp? Seccomp is a sandboxing tool in Linux. And what it allows you to do is actually when your application starts, before it actually does anything useful, the application can declare its intent to the kernel. It's some kind of, seccomp is kind of contract where an application can say, I will definitely use one set of system calls, but I will never use other set of system calls. Why it's useful, let's check an example. Imagine you're writing, it's like a toy example. The real life is much more complex, but imagine you're writing a simple clock application. And seccomp is a Linux feature, so your clock application will run on Linux. So before you even do something useful, when your application starts, you tell the Linux kernel, hey, I'm a clock app. And because I'm a clock app, I don't need anything from you except the time. I will only ask the time from the kernel. And when your application executes, at some point, it asks the kernel for the time, and the kernel responds properly, right? However, imagine you wrote your application in an unsafe C or assembly, and your application got hacked, right? And then the attacker tries to extract some private data and send it to their host somewhere on the network. So it makes like some kind of code execution, uses some code execution and tries to make your application send data over the network. But because Linux now see you broke your promise, you broke your oath, you're dead. So seccomp greatly limits the potential damage of remote code execution exploits. And it's zero cost overhead, right? So of course, if your application dies, that's an infinite performance drop because your application doesn't run. But it only happens if your application misbehaves. If your application behaves as it is intended, so you will get no security overhead. It also improves development velocity. Sometimes, because when you declare your intent to the kernel, you declare what the application is intended to do. But we all know that software runs how it was programmed to run, not how it was intended to do so. So you always have bugs. And then you can, if your application suddenly crashes, that probably it somehow behaves not the way you intended it to behave. So seccomp just sometimes helps to find bugs in software. Good? Any disagreements here? So all those things are examples of zero-cost security. Now we're going to talk about, there are security features which actually improves performance. And here we'll probably more focus on performance in the narrow sense. HTTP 2. Who heard about HTTP 2? Yes. A protocol was adopted as an internet standard in 2015, and it's a major rewrite from HTTP 1, which is almost 30 years old. We will celebrate 30 years next year, yeah. Unlike HTTP 1, it's a binary protocol. HTTP 1 is a text-based protocol. It does connection multiplexing. So in HTTP 1, you had to have the underlying L4 connection for each HTTP connection. For HTTP 2, they can reuse the one layer 4 connection for many HTTP 2 connections. And they also have these nice features called server push, where like HTTP 1 is like request response button only. In HTTP 2, server can proactively push resources which it's sure the client will request anyway. And there is also HTTP 3, by the way. It's still not standardized. It's just it's another improvement, and where HTTP 2 still uses TCP as its transport layer, HTTP 3 uses UDP for different reasons. When we originally deployed our first version of HTTP 2, we decided to measure performance, and this is like, these numbers are from 2015, so it's our first implementation of HTTP 2. And even then, our homepage, our company's homepage, received like a 100% performance boost, like average page load time decrease by half if it's loaded over HTTP 2. There is another interesting demo which visualizes the performance HTTP 2 might bring to your service. So like you see a side-by-side comparison how a big resource loads over HTTP 1 versus HTTP 2. Good? why not have it, right? So there is one thing. HTTP2 available only via TLS, right? So although the standard itself does describe plain text HTTP2, there are no implementations which implement plain text HTTP2. So if you want to HTTP2, you need to enable TLS, right? Of course, you can implement your own implementation, but then like you consider the balance here, like the easiness of enabling TLS on your service or re-implementing the whole layer 7 protocol. So it's a no-brainer. Speaking about TLS, who here doesn't know how TLS works? So TLS is a security protocol over layer 4. So this is a typical TLS handshake. Here, it's not that easy. So the blue part is a layer 4 TCP part. So in TCP, you have the three-way handshake, SYN-ACK and SYN-ACK. And then the TLS handshakes are. Why do we need a TLS handshake? TLS has been there quite a while, and it allows for different options and cryptographic algorithms to be used. So that's why you need a handshake to actually, for the client and the server to negotiate which specific crypto in particular they'll be using for that session. In TLS, and it happens on this stage, like a client hello and server hello modes. And in TLS, you get the cipher suite, so it's like a combination of key agreement. So client and server agree which key agreement algorithm to use, which digital signature algorithm to use, and which encryption algorithm to use. So the interesting part is digital signatures here. So, and there are only two options nowadays. So you can use either RSA signatures or you can use elliptic curve signatures. So RSA signatures are this older crypto system. It was originally published in 1977. It's security based on the hard problem of factoring large numbers. However, sub-exponential complexity cracking algorithm exists for RSA now. Well, in simple words, sub-exponential means they're not efficient yet, but they're very close to being efficient. And that's why, to make these algorithms unusable in practice, we have modern RSA has very large key size. So that's why you should never use RSA smaller than 2,000-bit keys. In contrast, ECC, they call it the newer crypto system. Well, newer, it's 1985, to be honest. And it's based on a different problem. A hard problem is based on a discrete logarithm problem over elliptic curves. And because it's a different problem, there are currently no even sub-efficient cracking algorithms exist for ECC. And that's why you have smaller key size. Like today, people use roughly around 256-bit keys. Okay, let's compare performance of these, right? I ran it basically yesterday on one of our servers, and here are the numbers. How many signs per second can each algorithm do? And we can see that ECC signs, and signs is what you care about on your server because your server creates signatures, is 15 times faster. So in the end, if you switch from RSA to ECC, you get faster TLS handshakes. You get less CPU utilization. I'll just come back to that in a moment. You get less key storage because keys are much smaller. And as a side effect, you get better security because ECC is just inherently more secure, right? And more on CPU utilization. So we did this measurement in 2017. So our TLS implementation, we use Google's Boring SSL. And the interesting part, and on one of our data centers, we measured like which crypto algorithms are used during the TLS handshake and how much CPU we spend on them. And the interesting part is here. So if you see during our measurement, we see 3/4 of TLS connections used elliptic curve cryptography, and only half the quarter used RSA. However, we also measured all the CPU time we spend in the boring SSL library, the crypto library which implements all of this. And from all the time our CPU is busy executing boring SSL code, almost 50% of that is spent doing RSA. And only 8% is doing elliptic curve cryptography. So 8% of CPU time serves 3/4 of signatures, whereas 50% of your CPU time in crypto serves only a small part of RSA, and there is also a little of RSA here. So switch to ECC, you get instant performance boost and less CPU utilization. Most people use RSA because they're afraid for compatibility, so that some clients might not support elliptic curve cryptography, but actually most modern TLS server implementation actually allows you to provide a fallback. So basically, because it's the server who decides which algorithm to use, so if the server detects the clients which support elliptic curve cryptography, it will use elliptic curve cryptography. If the client does not advertise it supports elliptic curve cryptography, the TLS server can fall back to ECC. So compatibility is not the issue here. Okay, let's go from a small server to the internet. Who knows how internet works? Who doesn't know how internet works? So this is the internet. It's a little bit bigger than that, but actually the point here is internet has no centralized system, right? So it's very decentralized. It has no Skynet you can blow up and get humanity back. So it's very distributed. And internet is basically a network of networks. It's connection network just interact with each other. In internet terminology, these separate networks, they are called autonomous systems, right? And the way how they communicate is via a protocol called BGP, Border Gateway Protocol. Why do they need to communicate? For your packet to travel from point A to point B, it needs to know the path. And intermediate nodes on the internet need to know who has specific resources, or basically IP addresses. So they do it via announcements. So like different autonomous systems announces which IP addresses they have. So like we have like one autonomous system, which is basically Cloudflare, because we now own this nice IP, announces we have 1111, and there is another autonomous system which announces it has 888, so it's Google. And you don't only announce the systems, the IP addresses you own, you also announce your neighbor IP addresses, because you might be an intermediate layer where packet traversing. And the point is this whole thing is not static, right? So the configuration continuously changes on the internet. So these announcements come and go, and sometimes, and in the end, you get what's so-called packet switching. So to reach from A to B, your data doesn't always traverse the same path, so because these announcements continuously change, right? And in the end, they may reach your destination through different paths. One of the major drawbacks, like BGP is quite old protocol, that originally didn't have any security, right? So it's all these announcements are based on like a gentleman's agreement that you kind of like your neighboring networks expect you to announce what you own, and they expect you don't announce what you don't own. Right. And of course, this leads to like bad actors appearing on the system, and they try to announce addresses they don't own. It doesn't always create like complete network failure, because packets traverse different paths. So some packets may go here, and some packets may go here, and like what this connection is concerned about, you just get some packet loss, but it's not critical. It's just like the network throughput is bad. So internet people came up with this thing called RPKI, which stands for Resource Public Key Infrastructure. And what it basically means, to combat this scenario, you now sign your announcement, right? You provide a clear cryptographic proof that you own this IP address, and your neighbors are expected to check this cryptographic proof before they accept your announcement and consider it valid. And this is a nice feature, and it basically allows you to remove these bad actors from the network. So yeah, RPKI prevents bad actors from claiming resources they don't own. But bad actors, these false claimers are not always bad actors. Sometimes you announce invalid routes because you have bugs in network equipment and software. You also have, like, all this network equipment is configured by real people, and people make mistakes. So they are like network equipment misconfigurations. So in the end, why does it not work? When you deploy RPKI for security, you kind of improve network throughput because you prevent this misconfiguration to have any effect on the internet, and thus you kind of like make things faster. Like, so yeah, and some misconfigurations cause severe outages. One example we experienced in Cloudflare in this blog post when a small US provider called Verizon announced incorrect routes and like shut off like half of the internet. But the minor misconfiguration take place all the time, and you get some packet loss here and there. It's usually not very impactful, but it just decreases your the performance. So RPKI in place, these misconfigurations do not happen, or they're just not valid. Security improves performance. The final thing is, let's talk about performance in the broader sense, right? This is a final example of, if you can't find performance improvement in the narrow sense, sometimes you can get performance improvements in broader sense. Again, this is Cloudflare Network with the map you can't see, but it's available on our website. It's like a regular world map. There's nothing special about it, right? And we have a lot of these data centers, more than 200 data centers. They're all physical, real hardware. Most of these locations are co-location, so we own the hardware, we don't own the data center. And many of Cloudflare engineers actually never visited. There are data centers we never visited, right? So like, we just send the hardware there, it gets connected remotely, and we start using it. So we have to provision a new data center a lot. And it's kind of like very time-consuming operation. So first we need to connect hardware. It's done for us by the data center staff. But then when we take over, we need to go through this very intimate process called verify hardware, which basically, because unlike in cloud storage providers where you get a nice interface for AWS, we have nothing, right? We just have hardware somewhere. So we need to set up initial network connectivity. We basically need then to manually configure the out-of-bound interface, which if you deal with hardware called BMC sometime. They usually come from the vendors unsecure, so you need to actually secure the out-of-band interface by manually going and clicking buttons. Then, when we have a secure out-of-band interface, we need to dump all the serial numbers from the remote hardware. Then we need to cross-check the serial numbers with our inventory system to actually make sure we're dealing with the hardware we expect it to be. There is no missed hardware. We received all what we want. It's in the right place at the right time. And then when we're done with it, so we do initial key provisioning. To efficiently manage servers remotely, you need some kind of SSH or configuration management system. And that usually comes up with using some public key cryptography. Each server should have a unique public and private key pair. So yeah, you need to push those keys into the server and connect them to configuration management system. Like for the record, in Cloudflare, we use Salt Stack. And then when you connect to that server, you need to verify key fingerprints over secure out-of-band channel to ensure it's all secure. All right? And you have to do it for each server in the data center. Some data centers are small, some data centers are large. And in the end, your operations team is like crazy. So what is a TPM? Who knows what is a TPM? Okay. Actually, each modern server laptop has a TPM. It's a tamper-resistant crypto chip in modern laptops and servers. Like any other crypto chip should do, it can provide you secure key storage and hardware random number generator. But actually, the most useful point about TPM, it's a fundamental building block for a thing called remote attestation, which provides you two things. It's authenticated identity for remote system and trustworthy assertion about the remote system state. So the way how it works in practice, so imagine you have the verifier. So for us, it's our configuration management system. At any point in time, to any remote entity, it can you have your remote entity, remote server with a TPM. At any point in time, the verifier can send a so-called quote, a request to the remote entity. And what the TPM can provide is information about the identity. And also, it can provide the full report about the state of the system, which operating system it runs, when it was booted, and like whatever you can think of. It's like basically the full state of the remote system. And because it's a secure crypto chip, it can provide it in a secure manner. So it signs a response, the response is authenticated, and integrity is supported. So by the time we do this remote attestation, we're communicating with the right host. We know that we're communicating with the right host securely. And the remote host runs only authorized software. So we discussed secure boot at the beginning of the talk. This is like local thing. So server will not boot unauthorized software. But here, the TPM just allows the verifier, the remote party at the other end of the world, to make sure that the remote server runs only the operating system we tell it to run and not anything else. So after that, we basically can trust the remote host. So when you integrate TPMs into your provisioning process, what you get, you can get better automation. So this is what automation does. It verifies server identity. It verifies running operating system. It cross-checks serial numbers. So it actually, server itself can cross-check serial numbers because we trust it to do, because it runs our software. And the automation, because we have a secure channel, it can provision configuration management keys. It can push the configuration management keys. And basically, when configuration management system kicks in, it brings up the server and starts serving production traffic. What our engineers do at this point is drink tea, having a good work-life balance, or work on something interesting. So in the end, by employing TPM, which is a security complex, you get better automation, less room from human error and misconfiguration during the provisioning. You have faster data center provisioning because just robots are just faster than humans. It's our weakness, right? And you have more efficient engineering time because engineers can develop interesting new things instead of doing like the manual repetitive tasks. And as a side effect, I guess, you get better security, which is nice to have. Okay, that's all of the examples I had for now. So what we'll learn today is that some security does not always have to impact performance. Remember zero-cost security. There are many modern things where sometimes actually improves your performance. Security can if you can't make security improve performance in the narrow sense, perhaps looks for opportunities where security can improve performance in the broader sense, like process, cost, etc., etc. And this approach is actually useful if you're a security engineer and you want to drive and prioritize your work with the rest of the company. Like this dialogue performance by security is what the rest of the company understands. So driving security by performance, like describing better security in performance terminology helps your company to understand security better and helps you to get it prioritized and done. So try to adopt this approach and maybe you'll have an easier time at work. Thank you.
I just saw a list of things.
This is a buffer overflow slide, which shouldn't be there.
Okay. So, do you at Cloudflare use all these things?
Yes, this is all things we use. This is just.
Do you have any more? Maybe some secret tips, that you can share, but we won't tell anyone.
Yes.
Oh, you see?
Let me see my secret slide.
Okay.
I also wanted to mention nice firewall. Firewall also improves performance. You kind of waste CPU cycles on the firewall, but if you implement the firewall properly, it will block bad traffic from the rest of your systems. So consider a case of a non-malicious zip bomb, right? So there are like certain archives which basically like can clog your CPU, but if you block them early in the firewall, your CPU will not be wasted. And they're broken anyway, so no need to process them. So like proper firewall is a nice example of, I would say I think it's performance in the narrow sense.
Yeah, it's like a filter. It works like a filter, so you just waste, you waste some performance outside of your network to get better performance inside of your network. Makes sense. Do we have questions? I have a microphone and we still have a couple of minutes for questions. Questions? What are, do you use any of these things that Ignat mentioned? HTTP2, okay. Full disk encryption probably?
Yeah.
Usually it works just by default. Okay. I don't know about TPMs because from my perspective, TPM provisioning, this is something that should be set up on your data center. It's not something you set up as engineer for your software, right?
Oh, you don't need to provision TPMs. TPMs come with, you can add your own keys to the TPM, but TPM also has a manufacturer baked in so-called endorsement key, which is actually used for remote attestation. So you put your own keys for secure storage, but for remote attestation, a vendor puts a key there and a certificate, so you can actually verify the TPM's public key back to the vendor. And then what you need to have in your when the vendor ships you like serial numbers and other data about the systems you're buying, they also send us the TPM public key, so we can track which TPM was installed in each server, and we can cross-check it remotely easily.
Yeah, but I mean, for developers, it's just we have TPM, let's check they're valid, fine. We have a remote attestation, and we don't spend any time on that. I like security things that, as a developer, I don't need to spend time on.
Who definitely knows they use elliptic curve cryptography in TLS?
I think many people...
There is one question over there.
Do you have a question? Awesome. Just give me a second.
Thank you for that. I've got a question about data encryption. So have you got any tips around sort of runtime encrypting data for storage, like maybe long-term storage or anything like that?
You mean the overhead?
Yeah, any sort of performance optimization.
So I just urge you to go to my link and to my talk, and the slides have a full like test case A and B, and it's actually, I didn't do it like on a production server. I did it I posted all the comments so you can retrace the steps on your local laptop and you can immediately see the overhead. The problem which we encountered, that implementation of disk encryption in Linux kernel was not very efficient. The architecture is a bit old in terms of the architecture is basically considered spinning disks, which were like 10 years ago, and now everyone is using SSDs or NVMEs. And basically, there are some other things in the Linux kernel which didn't work properly, so they made workarounds. But now these things work properly. These workarounds do not need anymore. Is not needed anymore. So it's the most of overhead comes not from crypto itself, but the way how it's all like tied together. To give you some numbers. Our patch on my test scenario improved the throughput by 100%. So.
I'm kind of thinking about like field level type encryption. So like maybe if you wanted to encrypt an email address or something, but not the whole set of data. Is that something you got any experience with or tips around?
So again, selective encryption is mostly useful if the crypto is expensive. But crypto is not expensive. It's the way how you implement it and wire it up, it's expensive. So sometimes you may end up overcomplicating a system and spending more time parsing your data, looking for email addresses to encrypt them, rather than just encrypt the whole thing sequentially.
Cool, thanks.
Thank you. Here is a sticker. Don't roll your own crypto. Great questions. And actually, like answering the question about field level encryption, because like we do it a lot. Usually, what we say that if your software runs on JavaScript, or PHP, or Ruby, or Java, you won't notice cryptography, because as Ignat says, all the details of your application, all the network calls will be more expensive than cryptographic computations itself. But it also depends on the architecture, on the data flow, and what we see when we re-engineer application to add cryptography, especially field-level selective encryption, where you need to encrypt only some of fields. Sometimes you need to end up to re-engineer the data flow of your system and to avoid, like select all calls to your database, but just to distinguish like reading flow, writing flow, reading plain text data, reading sensitive data in a different way. And in that case, you can have better security because you can monitor, you have the different data flows, and you can monitor which behavior is normal and which behavior is anomaly behavior, and you can have even a performance boost because you don't do all these operations in one call as you used to do before. Okay, any more questions? Discussions? One. Okay, yeah, I see. That's complicated. Yeah.
Thank you. Are you ever worried that the hardware you receive from a manufacturer has been tampered while in transit? And if you do, how you?
Can you repeat?
Do you ever consider that the manufacturer or the hardware you receive from a manufacturer can be tampered in the transit?
Yes. This is why we want TPMs.
Huh? Because last year there was an article in Bloomberg about some doomed scenario about chips and things
yeah, the Supermicro thing. That article wasn't proved actually. We definitely consider the possibility when the hardware is in transit, it can be tampered with. So that's why TPMs are quite helpful with that, because that's why we cross-check the serial numbers and everything. So depending on the complexity of the attack, you can basically, you can receive a hardware with different network card, right? So if the attacker was not that sufficient, it will have a different MAC address. But and that's why TPMs are useful, so you can at least cross-check the hardware wasn't tampered in transit in some extent. Yeah.
It's a follow-up of that, because that was sort of my curiosity as well. What if you have? How do you trust the TPM vendor to not be nation-state compromised?
That's a good question. You have to. So unfortunately, it's the way how trust works. You can't create trust from out of thin air, right? You always have to have a trust anchor. So that's why it's called trusted platform model, not trustworthy platform model. So there is something you need to implicitly trust, but from that trust you can start building your trust chain to make other systems trustworthy. But like that initial trust, which usually called trusted based, you have to implicitly trust it. So to use trusted platform model, you have to trust the TPM vendor. To use our servers, we can check if they were tampered in transit, but what if like our vendor is tampered, right? So, but we have to trust it, and currently there is no way, unless you build everything, you're willing to spend the cost, build everything from scratch, your own server, but then you have to trust the vendors of all the components, and it goes to an infinite like loophole.
Yeah, this is how trust works, yeah. Okay, let's wrap up. Thank you for your questions. Thanks, Ignat.